Certainly. Here's a narrated script on graph neural architecture search for automated design of scalable message passing schemes in heterogeneous networks, crafted to be both comprehensible and engaging for a broad audience. Imagine you're organizing a festival in a city with neighborhoods that all look completely different. Some are traditional, others are modern, and a few are business districts. You need to deliver unique, complex instructions to every group, but you have no prior map, no knowledge of the best routes, and no single set of instructions that works for all. What's the smartest way to guarantee that every important message gets to the right people, in the right format, so the festival is a roaring success across every corner of the city? This gentle chaos is a lot like the world inside certain computer networks called heterogeneous networks. Today, I'll introduce you to a hot and powerful concept in AI called graph neural architecture search, or GNNs, and show how it helps us design automatically scalable and intelligent ways to pass messages through these wildly diverse networks. Let's break that down. We'll start with what it means, why it matters, how it works on a basic level, a few examples where this technology is game-changing, the larger implications, and a couple of natural questions you might have along the way. First, what is this topic really about? Let's imagine a network, which, just like our city, has very different types of neighborhoods, or in technical terms, different types of nodes and connections. Facebook, for instance, isn't just people friends people, it's people liking pages, people checking in at locations, people joining groups, and so on. That's a heterogeneous network. And suppose we want to understand, summarize, or make recommendations involving these complicated, multi-relational data structures. This is where graph neural networks, GNNs, come in. At a high level, GNNs are a way for computers to learn by passing information along the connections in a graph, similar to how word of mouth works in a city. Each person tells their friends, they tell their friends, and so on, so that ideas or information can spread efficiently. But, and here's the problem, unlike simple networks, heterogeneous networks have many kinds of relationships and entities, so a one-size-fits-all message passing strategy fails. What works for a person-person link may flop for a person pointing to a business or person liking a post, for example. Now, the classical approach would be to have expert engineers design special message passing recipes for each kind of network. But that's time-consuming, subject to human error, and not always scalable as these networks grow more complex. Enter our hero, graph neural architecture search, GNNs. Imagine if you could create thousands of possible postal routes and mail delivery strategies for your city using a computer, test them in simulation, and let the machine not only pick the best messenger but also design entirely new ones you hadn't considered before, adapting for each unique neighborhood pattern, so everyone gets their message efficiently. That's GNNs. It's like sending thousands of hypothetical mail carriers into your festival city, each with a slightly different approach, and letting an automated system iterate until only the best strategies survive. Technically, GNNs uses algorithms, often inspired by natural evolution or trial-and-error learning, to automatically generate, evaluate, and improve the underlying architectures, or blueprints, for how information gets passed in a given heterogeneous network. Instead of manually deciding how, say, an influencer's recommendation should trickle from person to group to event, the system searches over a huge array of schemes, testing which ones help computers predict or understand the network more accurately and efficiently. To keep this concrete, let's look at a couple of scenarios where GNNs shines. Take online recommendation systems, think of Amazon or Spotify. Behind the scenes, the system deals with people, products, reviews, and categories, all connected in countless ways. Using GNNs, these platforms can automatically discover smarter ways to connect your interests to surprising new products or songs, spotting unusual but meaningful relationships a human designer might never think about. Or consider fraud detection in financial networks. Banks have to track transactions between people, companies, devices, and accounts, each with a different role and set of connections. An automated GNNs approach allows the network to find the most efficient way for information about suspicious activity to spread across the network, improving the detection of unseen fraud rings or money laundering chains. A third example is in large-scale knowledge graphs, like those powering virtual assistants or search engines. Here, nodes could be people, places, events, articles, all tied by myriad relationships reminiscent of our diverse festival city. GNNs can discover unique, scalable message passing strategies that help these assistants answer complex questions or suggest the right content, no matter how complicated the underlying network gets. So, why does this matter in the big picture? First, it democratizes and accelerates progress, no more needing scarce experts to handcraft every aspect of new network models. It allows computers to adapt the best strategies as data grows and changes, and it can reveal entirely new insights about how to design AI systems for the modern, messy world of real data. Moreover, the automated, scalable aspect means the same framework can handle tiny social graphs or global networks with billions of nodes, without a human overhaul every time things change. Now, you might wonder, does this make engineers obsolete? Not really. Instead, engineers are freed from the grunt work of endless trial and error and can focus on higher-level innovations, fairness, ethics, and deploying these systems responsibly. Another question, will we ever see this in familiar products, like ChatGPT? Well, while ChatGPT isn't itself powered by GNNs, the underlying knowledge graphs and recommendation engines powering features in search, social networks, and content curation can absolutely benefit from these advances, making them smarter, faster, and more adaptable. As we look ahead, the promise of GNNs for heterogeneous networks is exciting. It marks a shift from rigid, handcrafted models to evolving, self-improving systems, just as cities have gone from static layouts to dynamic, smart infrastructure that adapts to the needs of citizens in real time. As AI becomes part of our everyday infrastructure, tools like this will help ensure solutions are both robust and agile, no matter how complex the world gets. In summary, by letting machines design their own message-passing blueprints for ever-changing, multifaceted networks, we're opening the door